and then we have the, in order to have the time domain analysis, we'll go for the cathode ray oscilloscope. And then in the frequency domain, over 80% of the DSP applications require some form of frequency domain processing. Any form can be produced by adding a sine wave together. So here, one particular important concept that we should remember, that so the output of any particular the input is, it is the, what we can say, convolution of input it its impulse. So that's why there is a correlation between signal processing and a Fourier series analysis. So in the Fourier series, what we are doing is we are trying to represent signal, the Fourier series representation of a particular signal in terms of its sine and cosine terms. Similarly, in the case of signal processing, what we are doing is we are trying to represent the signal in terms of its input and impulse response. So that's why, so the convolution of input with its impulse will give the response of a particular system. That's what we can call it as a linearly constant difference equation. From the linearly constant difference equation, I will try to express the system in terms of input and output. From the particular input and output, we can get a system function. So this is the way how we can analyze the signal in terms of frequency domain. So there are certain relations. And now coming to, after having the idea about the signal, now we will come to the system. So system is nothing but it is an entity that responds to a signal. So when you take a particular system, so corresponding to the input, there is some particular physical phenomena that should occur in a particular system, and corresponding output that we can get it. So here we are seeing that a fundamental examples of RC combination circuit. Then there is a camera. So from the particular the light, the signal is converted into a image. Then speech recognition. So these days actually laptops, when you take the laptops, so there the fingerprint recognition has come, then iris recognition has come. So for a particular input, so whatever the input that we are considering, corresponding to the input, there should be some response that we should get. So as we have seen that a signal, the corresponding to a signal, an entity that responds to a signal is called the entity. Okay, so similarly the we have different types of examples of a system: mass spring, tank, cell phone system. Okay, then this is actually an example for a system where when I am talking the from a particular transmitter, that particular information should go to the at the receiver end. So there is electromagnetic signal transmission should be there, then through the optical fiber, then I can get a particular output. So there is some particular physical phenomena that should occur, and from the physical phenomena I should get a output. So this is one particular example of a particular system. So similarly, how we have the classification of the signals, we have the classification of the systems also, like continuous and discrete time system, linear and non-linear system, time variant, time invariant system, causal, non-causal, stable, unstable. So I am not touching all these particular things because these are the examples of different types of systems. Coming to the real world signal processing. So any type of a signal processing, when you consider, there are two particular domains that we have. One is called the analog domain, another one is the digital domain. Suppose if I want to find out the room temperature, or if I want to find out the pressure, so that is basically a physical quantity that we will try to find out with the help of a tachometer. And from the tachometer, I'll try to find out that particular physical quantity. I'll try to convert into an electrical signal. And there actually, in order to convert a physical quantity into an electrical quantity, what I'll do is I'll try to use a transducer. As you know that a transducer, it's a device which will convert from one form to other particular form. Once if I convert the physical quantity into an electrical quantity, then that particular signal, suppose if that particular signal which is having the less amplitude, then if it is contaminated with the what we can say noise, then in the analog signal processing we'll try to process this particular signal. So once the analog signal processing is over, then this particular analog signal is converted into digital. So once if you get the digital, then digital signal processing unit will come into picture. There we will try to use different types of DSP processing uh, techniques that we will try to use. I'll try to tell what are the DSP processing techniques, very fundamental techniques that we will try to use it. From the DSP techniques, I'll try to process that particular signal. I will get a digital domain. Then the actually the end user is in terms of the analog. So that's why what I'll do is this particular analog again it will be converted into digital. There are different types of ADT converters are there, the DTA converters will be there. So with the help of those things, I'll try to convert. So any real world signal processing which consisting of analog domain and digital domain, I'll try to process the signal from analog to digital. So these are where we can use the signal processing. Lot of the what we can say the advantages of this particular signal processing. The pictures itself touches different types of applications. Okay. Now coming to the what are the different types of what we can say the operations while doing this particular signal processing. So we can see that spectrum analysis, digitization, reconstruction, compression, then storage, okay, then modulation, then prediction. So these are the what we can say operations in order to process the signals we will try to use. So this particular signal processing, it not only restricted to one particular domain, but it also the useful in the case of communication systems. So I'll give one example. Normally, in the networking computer networks, we know that two types of networking. One is OSI ISI reference model. Other one is the TCP IP protocol. In the case of the OSI reference model, we have different types of layers. See here, the physical layer, data link layer, network layer, transport layer, then session layer, presentation layer, application layer. So in all these particular layers, so we can see that in the case of the presentation layer and in the case of physical layer, so there are certain signal processing techniques people use. One is the analog to digital conversion, data compression, source coding, and then we have the modulation, equalization, multiplexing. So these are the different types of what we can say the signal processing techniques that we can use it even in the case of OSI reference model. So in the case of the 7 layers of OSI reference model, uh, we can use this particular what you can say signal processing domain in this particular networking system also. So why I am showing specifically this particular reference model means the people most of the time people think that this particular signal processing is applicable to some particular domain only. Not like that. This signal processing is useful in all the particular cases. And coming to so why do you want to go for the signal processing? Why do you want to go for the signal processing? So the purpose of the signal processing operations are varied. So one is the signal analysis. So that means the second one is the signal decomposition, then feature enhancement, noise reduction, then signal compression and signal encryption. So these are the major operations, or we can say that rather the advantages why we want to go for this particular signal processing. So the first one is the signal processing. So in the case of signal analysis, in the case of signal analysis, what we can analyze So irrespective of type of a signal, though as we have seen in the beginning, there are different types of signals we have, like ECG signal, speech signal, radar signal. So in all these particular signals, if you want to analyze a signal, how do I can analyze from transitions, then patterns, peaks, frequency, distribution. So from all these particular the parameter the patterns, I'll try to analyze the signal. So the second one is signal decomposition. Signal decomposition means separating the message or message and noise. So there are two types of basically when you take a particular the signal, so signal is contaminated with the noise. There are two types of noises are there. So can anybody tell me what are the two types of noises?
సార్ స్క్రీన్ షేర్ అవ్వట్లేదు సార్.
షేర్ అవ్వట్లేదమ్మా.
Sir, your screen is not visible to me, sir.
1 minute, 1 minute. Now?
Visible, sir, now.
Is it visible, Amma?
Visible, sir, visible.
Okay, okay. And madam asked actually, screen is not visible. Just now she asked. Hope I think everybody now you can see the particular slide. Okay? At least one or two, please respond.
Yes, sir. It's okay, sir. Now.
Okay. So basically the purpose of signal processing operations are varied. Some of the most important ones are, one is signal analysis. So in order to analyze the signal, as I told you that from the transitions, patterns, peaks, frequency distribution, I can analyze the signal. Then second one is the signal decomposition. In the case of decomposition, as I told you that any type of a signal which is contaminated with particular noise. So what are the different types of noises which we can come across a particular signal or a particular system? Can anybody tell me? Can anybody tell me, suppose if I have a particular signal, what type of noise that we can come across? Or if you take a system, what type of noise that we can come across? Is it audible? Is it audible?
Yes, sir.
Yes, sir.
Please. Tell me, anybody, can you tell me what type of noises that a particular message or a signal which is contaminated? Generally.
Internal and external noise, sir.
Yeah. So internal and external noise, what are the other name for that?
Internal, like
Thermal noise and
No, that is okay.
quantum.
Internal and external, that is correct. But that internal and external noise names are, there is exogenous noise and endogenous noise. Okay, exogenous and endogenous noise. So within the internal circuit, we can have different types of noises. Okay, and externally, because of the external effects, we can get another noise. Okay, so as you said, there are different types of noises like short noise, thermal noise. Okay, so transmission line effect, random noise. So there are different flicker. Okay, so there are different types of noises. So our goal is actually we need to separate the actual message and noise. So this is the major crux of this signal processing. Any application when you take, either it may be image processing, it may be speech processing, it may be radar processing, or whatever the processing that you can consider. Ultimately, our goal is processing of a signal means removing the noise. So if you want to remove the noise means I need to decompose the signal. So the decomposition is very, very important criteria. So that's why everybody they are talking about nowadays machine learning, artificial intelligence techniques they are using. So the majorly the machine learning technique, what is the use of machine learning technique in the signal processing? If time permits during the course of the other sessions, if there is any facility, I'll try to talk about machine learning, how it is useful in the case of signal processing. That is different type of domain. There is supervised learning, unsupervised learning, then enforcement, the machine learning concept is there. So ultimately, actually, there also what they are doing is they are doing certain type of decomposition only. That means the signal decomposition is one major, the what we can say, the application I can use as a classifier. So in the machine learning itself, the deep learning, what we are talking, the classifying, how best I can classify my particular signal, or how best I can classify my particular, what we can say, feature. Because the hidden features also I should be in a position to classify. So one example I can say, the separation of the message and the noise, I can use the filtering concept. Then I can use, as I said, the machine learning approach. If I want to speak, I can use the principal component analysis like PCA, ICA, like that people are using. What is principal component analysis? Majorly, it will do, depending upon certain criteria, I will try to divide the particular the feature into subsections. So there is one particular problem. That particular problem I'll try to divide into subsections based on certain categorization of the feature. So like that, I can separate the message or a message and message noise. So this is the major thing that we can observe in the case of signal processing, that is signal decomposition. So first one is the signal analysis, second one is signal decomposition. So that's why I have told that signal analysis, again there are two different types of approaches. One is time domain analysis is there, frequency domain analysis is. Nowadays actually there is what we can say, the the another the time domain masking concept is there, frequency domain masking is there. Like that, different types of approaches are there. So now there are other type of signal processings are there. There is social signal processing is there, there is a sparse signal processing is there, adaptive signal processing is there, multi-rate signal processing is there. In all these things, ultimately what we are doing is we are trying to analyze the signal depending upon its feature. So the first character of why do you want to go for signal processing means signal analysis. The second one is signal decomposition. So most of the people they will tell, suppose if I want to do research in signal processing, what is the area that I need to consider? So the major thing is you can take either signal analysis or signal decomposition. Lot of research that is going on. So if you search what are the different approaches in the case of signal analysis, you can get n number of approaches. You can take one particular analysis. You can compare different types of analysis, and what is the novel approach, what is the your proposed approach. You can bring out the research direction. Similarly, signal decomposition. So from the beginning, how we are signal decomposition, the major thing is, as I told you, that the signal processing, I can define that in terms of signal decomposition. The signal decomposition origin, it comes from the Fourier analysis. There, in the case of Fourier analysis, what I am doing is I am representing the signal in terms of its sine and cosine terms. Similarly, in the case of the signal processing, what I am doing is I am representing the signal in terms of the signal and its impulse. So in the case of signal decomposition, I am separating the signal in terms of its signal and noise. So these are the two challenging tasks. Wherever if you take, These are the two fundamental research topics. Even though for looking, these two are very simple things in your mind, because every time we are hearing that, but there is lot of research, the depth in these particular aspects. Then the third one is feature enhancement. So why do you go for the feature enhancement? As we have seen that when we are converting a signal, the what we can say that a physical quantity into an electrical signal, then naturally the particular signal which consisting of a weak strength, then it is contaminated with the noise. So we need to boost the signal characteristics. So in other way, I can say that signal, or I can say a feature. So we need to enhance that particular feature characteristics. So that's why we will try to use different types of what you can say in any particular signal processing or a instrumentation block. There is pre-emphasis circuit will be there. What is the purpose of pre-emphasis circuit that we will try to use in any particular instrumentation system or in any particular signal processing domain? The basic idea to keep this particular the pre-emphasis circuit is in order to enhance the the features. What are the features that I need to increase is signal components. Then suppose if it is the image, then I need to sharpen the image. So that's what we are seeing that when you take the, let us consider an example of image processing. So normally in the image processing, suppose when I am talking about these days, actually the case of biomedical signal processing, people used to detect the tumor detection. Okay, when they want to find out the tumor detection, first what they will do is they from the data, they need to take the different types of images of the tumors. Okay, so then from the characteristics, they need to identify the area of that particular tumor diseased area. So that means they will try to take up the region of interest, ROI. So everybody heard about that particular feature, ROI. So once if they find out that particular ROI, this region of interest which is contaminated some particular different types of noises. So we need to remove that particular noise. So there we need to sharpen that particular image. Once if we sharpen that particular image, then I can find out the characteristics. So that's why the feature enhancement is very, very important in the case of what you can say biomedical signal processing. Then another one I can say that in the case of we did one particular project, synthetic aperture radar. So these days actually from the satellite we will take the images. So weather forecasting, or suppose in the deep forest area, if there is any particular the suppose terrorist attack is there, or some particular if you want to identify some particular object. So what we will do is we will try to take different types of images. So then when you take that particular images, so we need to what you can say naturally that particular images are not clear, they are blurred with different types of noises. So we need to sharpen that particular image so that I can see the perfect object. So that's why there also I can use this particular feature enhancement. So the first one is signal analysis, signal decomposition. Then third one is the feature enhancement. Fourth one is noise reduction. So noise reduction means here, as I said, different types of noises is there. We need to reduce that particular noise. So there are different types of noise reduction approaches. So that is also another what you can say the fundamental the research area in the case of signal processing. If it is a deterministic signal, there are number of filters that I can use. Even nowadays people are using different types of transform techniques. So by using the different types of transform techniques, I can separate the signal from its noise. Okay, so then suppose if it is a random signal, I can go for estimation. I can use different types of estimators. From the estimators, I can find out the noise. I can reduce the noise. Then the another one is the signal compression. This is also another important area. Signal compression means here. So now here I need to use the less bandwidth. I need to transmit effectively. So in such case, signal compression comes into picture. How best I am compressing the signal without degrading the quality of the signal. So there the signal compression will come into picture. Next one is signal encryption and transformation. So signal encryption and transformation means here. So I need to, what we can say is, I need to maintains the secrecy and I need to transform the signal. So what are the different techniques of the maintaining the signal encryption methods, and then how best I can transform the particular signal. So this is actually another domain. So now if you see here, I have told 6 different types of operations or 6 different types of purposes. Why do you want to go for signal processing? Again, I'll repeat. So please, anyone, can you tell me why do you want to go for signal processing? From girl side, loudly, can you tell? Is it audible?
Sir,
Is
sir,
it
it's
audible?
yes, sir, audible, sir.
Audible, sir.
Please, one of you tell me why do you want to go for signal processing? You just see the slide and tell me. Any one participant?
Yes, sir.
Yes, sir means tell me. Anyone? Why do you want to go for signal processing? Tell me. Are you observing the slide?
Yes, sir.
Yes, sir.
To extract some information from the signal, we'll do signal processing.
From watching the PPT, you please tell. Anyone?
Yes, sir. Yeah,
So that.
signal analysis we can do, sir.
Hmm.
We can do signal decomposition. We can do noise reduction in the signal.
Okay.
Signal compression,
Okay.
signal encryption and transformation.
Yeah. So please see that, because suppose if it is a offline program, we can interact each one. But since it is a online, it should not be a single side talk. How do I know that people are listening or watching? So unless if you reciprocate, then that will be better. It's not the question that whether you are listening or not, but at least so the the hard work that is done by the organizers, if some people, if they understand the concept, then that will be better. Okay, so that's why I asked, please concentrate and try to listen. So now, up to now, what we have seen, we have discussed about the signal, then system, then what is real world signal processing, then why do you want to go for signal processing. So now I am not going all these things. Signal analysis just simply give some exposure. This is the analog input from analog filter, then there is analog to digital converter, DSP algorithms. Here we can have time domain display, frequency domain display. So this is one example, signal spectral analysis, how we can represent. So this is the speech data. This is actually the spectrum. Okay, this is voice, the speech data. We lost the golden chain. So this is the way actually thing, and this is the spectrum of that particular the speech. Okay, so coming to the first signal processing. So when this first signal processing started means in the World War II, radio detection and the ranging radar. It is actually one of the first signal processing application. So here in the radio detection and ranging, So the people when they transmit when they want to if they want to know the target range and direction, what they will do is they will transmit a particular pulse and the received pulse. So from the received pulse, so they will try to, what we can say is, uh, they will try to find out the distance that is traveled by the pulse, and from these they can find out from where this particular target location and range. So that is actually the first signal processing. Okay, and now coming to here, now I'll try to discuss about different fields of signal processing. Okay, so this is somewhat interesting here. One is the statistical signal processing. So statistical signal processing means analyzing and extracting the information from signals and the noise based on their stochastic properties. This is about statistical signal processing. So statistical signal processing means, as I said, from the stochastic properties. So what are the different types of stochastic properties? Mean, mode, variance. So by knowing all these particular parameters, we will try to process the signal. That is called statistical signal processing. Statistical signal processing. So this is one particular domain. So in the statistical signal processing, we have the parametric estimation, what you can say, non-parametric estimation, different types of advanced Vinod techniques. Then we will discuss about what you can say, multi-rate signal processing, adaptive signal processing. Then we have there is a model-based signal processing. Okay, all those type of, what you can say, the order 3 higher order statistics, all these particular areas that we will try to discuss in the case of statistical signal processing. This is one particular domain. The second one is the audio signal processing, where in the case of audio signal processing, for electrical signals representing the sound such as speech or music, I can use this particular audio signal processing. Okay, so for electrical signals representing the sound such as speech or music, this is second one. Third one is the speech signal processing, for processing and interpreting the spoken words. Okay, I can use the speech signal processing. And again, in the case of speech signal processing, we have the speech production, speech analysis, then we have a speech synthesis, speech enhancement, then we have a speech recognition, speaker recognition, and speech coding. All these particular areas will come under speech signal processing. So where I can use the signal processing. So in the case of speech signal processing, there are two areas that I can use. One is the speech analysis. So analysis, the speech analysis means here, the we need to find out whether the speech contains the voice or unvoiced or a silence. So in order to find out whether the speech contains voice or unvoiced, what I'll do is I'll try to use different types of techniques. Like I can find out the energy of a particular signal. If the speech contains the energy, then I can say it is a voice signal. Suppose if I find out the average magnitude of the energy, so if there is any average magnitude of energy is there, then I can say it is a voice signal. I can use the autocorrelation method. From the autocorrelation method, if the signal is a output is a periodic signal, then I can say that it is a voice signal. If the output is a aperiodic signal, then it is not a voice signal, it is an unvoiced signal. So then like that, different pitch estimation, like that, different types of approaches that I can use, I can process the signal. That is one particular area where I can use this speech signal processing. Then the second one is I can use what you can say, in the case of speech enhancement. As I said, the feature enhancement, we need to remove the noise. In the case of speech enhancement, there are different types of approaches are there. One is called the perceptual modeling approach, and then statistical approach. In the case of statistical approach, I can use different type of the filtering concepts, and from the filtering concepts I can process the speech signal. So the another area is the speech signal processing. Then the image processing in digital cameras, computers, and the various imaging systems, I can use the image processing. So there are a lot of research. Everybody knows that this is a big ocean, image processing. So in digital cameras, so we can use this particular image processing in all other particular areas. As I said, in the case of radar signal processing, we can take the images and then we will try to process. Then we have a video processing for interpreting the moving pictures. For interpreting the moving pictures, I can use the what I can say, the signal processing concept. Then array processing for processing the signals from array of sensors. So array processing means here, there are different types of sensors which people can keep, and then uh, they will try to extract the information, and then from these particular sensors they will try to take the information, and then from this particular information they will try to identify the features. This is called the array processing. Okay, so we did one particular project with DRDO Chandipur, where we can keep different types of sensors, and we try to find out the acoustic, the sound from opponent side, and from this particular sound, uh, we try to find out the uh, the the opponent people when they are firing, from which particular direction it is coming. That we will try to find out, and based on that we will try to take a action. So that is the array processing. So then seismic signal processing, to know the earthquake, I can use the seismic signal processing. So where actually in order to protect the even tsunami, the earthquakes, so depending upon keeping some different sensors, we will try to find out the vibrations, and from these particular vibrations I can find out the what I can say, the whether there is some particular damage that is occurring or not, we can find out. So like that, these are the different types of fields of signal processing: seismic signal processing, array processing, then video processing, then image processing, speech signal processing, audio processing, then statistical signal processing. So these are the different types of the fields of signal processing. If you take the any particular domain, all these particular areas, again I am telling, if you want to pursue research, as I said, all these particular, what we can say, I told you that the this particular, what we can say, these particular signal analysis, signal decomposition, feature enhancement, noise reduction, signal compression, signal encryption and transformation, all these things which you can apply for these particular fields. Either I can use it in the statistical signal processing, I can use it in the audio signal processing, I can use it in the speech signal processing, I can use it in the image processing, I can use it in the video processing, I can use it in the array processing, I can use it in the seismic signal processing. So you should have some clear cut idea. If you want to do a research, you can take any particular field, whichever domain you want to take, and then apply that particular research domain, like signal analysis, what you can say, signal decomposition, other particular features that we can use it. Okay, apart from that particular thing, we have the DSP applications. So in communications, instrumentation, industrial control, voice speech, medical, pre-audio, consumer, military. In all these cases, the what I can say, the signal processing is useful. Okay, so these are the things, some of the basics, as I said, DSP, convolution, correlation, bilinear transform, discrete Fourier transform, jet transform. Okay, these are the very basic things, techniques that we can use DFT FFT, correlation. See here, from the correlation also we have different types of applications of correlation: cross spectral analysis, detection, recovery of signals buried in noise, pattern matching, delay measurement. These are other applications of correlation: calculation of energy spectral density, detection and estimation of periodic signals, matched filtering and targeting, determination of impulse response, determination of signal to noise ratio we can use. Okay, this is IR filter, FIR filter we can use. So these are the two digital filters. As I said, from the difference equation, Z transform, and we can have the transfer function and we can process. Similarly, FIR filter, from the difference function, Z transform, transfer function we can find out. Okay. So this is about the basic, what I can say, the introduction about the signal processing. Now coming to the some of the advances in signal processing. Is it okay? So up to now, please tell me,
Yes, sir.
is it okay? So I have given
Yes, sir.
the basic idea about signal processing, fields of signal processing, and then where we can use these particular things. Is it okay?
Sir, can you please mention the importance of deep learning in speech enhancement, sir?
Yeah, that is actually, that's what I told you, na. The other concept, actually, I need to take the machine learning and then different approaches, and then I have to go for deep learning concept. So
Okay.
I'll give one simple example. The deep learning actually,
Yeah.
so please, other people should mute your the voice. There is a disturbance that I am getting. So deep learning concept in the case of speech enhancement, you tell me specifically which particular area you are working in speech enhancement.
Speech enhancement, sir. I'm trying to, reduce the noise involved in original signals, sir.
No, that
Audio,
is
sir.
okay. That is
Okay.
okay. Speech enhancement means there are different types of approaches, madam. As I told
Okay.
you that statistical approach. So
Right. Some conventional methods are there, sir, like speech synthesis and spectral subtraction. So there
no,
are
no, no, no.
some
Please,
approaches
please.
now.
No. Listen. Speech synthesis is different, Amma. Speech
Okay.
synthesis concept is different. So there are different types of approaches. Basically, in the speech enhancement, I'll tell basic idea: spectral
Okay.
subtraction, as you said. So
Yes, sir.
spectral subtraction, we can. That is actually the fundamental approach. There, what we'll do is we will try to calculate the energy by using the fast Fourier transform. We can find out, estimate the signal energy and signal noise, and we will try to subtract. Okay, so from the signal, whatever the noise that you have estimated, we will subtract the noise, and then we will get a signal. That is spectral subtraction. Then there is actually signal decomposition is there. So in the case of signal decomposition, what we'll do is we will try to find out, detect the what you can say, singular decomposition approach, SVD, singular value decomposition. I've heard about singular value decomposition. Singular value decomposition.
No, sir. No, sir. No idea, sir.
Yeah, there actually you can find out what you can say, the uh, matrices we will try to find out. So larger the vectors, the singular vectors we will try to find out whichever the larger vectors oriented signal, which is actually original signal, and the lesser the vectors are the noises, we will try to eliminate. That is another one. Then we have adaptive algorithms we'll use, like LMS algorithm, least mean square algorithm, then recursive least square algorithm, then we have a Kalman filter algorithm. So normally these algorithms are adaptive in nature. So whatever the signal that is contaminated with the noise, so what we'll do is we'll try to apply to a digital filter. Okay, and then once if you process that particular signal, then we'll get some particular error. So this error again we'll try to feed back to the adaptive algorithm. So there I can use different types of algorithms. Anyhow, if time permits, I'll try to discuss. So by using the LMS algorithm, I can use this. Then, as you said, deep learning concept. So basically, we will try to divide the signal and the noise decomposition. So in such case, I can use actually even in the LMS, normalized LMS will come into picture. So when you are normalizing the LMS, so we need to take the features. In such case, I can take up the hidden layers of that particular features, and then I can process. There I can use the deep learning. So deep learning directly we cannot apply. In the case of normalized LMS algorithms, I can use this particular deep learning in the case of speech enhancement. That's what I need to talk about what is supervised learning, unsupervised learning in detail, and then you can come to that. But anyhow, be in touch. So definitely you can contact me, go through my website and talk to me. I'll try to give some idea. Okay, ma?
Sir, thank you, sir. Sir, I have one more doubt, sir. Sorry for the disturbance.
No problem.
Sir, first of all, is there any difference between STFT transform and S transform, sir? S transform.
Yeah. STFT transform is that is short time Fourier transform time domain, ma. Okay. S transform is a Laplace transform. Transform. So that means that is actually S domain. So that's why that is not in digital. So S domain is in analog. That's why what we will do is in the case of filtering, S domain we are converting into Z domain by using the Z transforms. You know that we will in the case of analog filtering. So when you want to in the case of digital filters, design of a digital filter, normally we will have a problem in the S domain. You heard about that? We will have a problem in 1 by S plus 2 or 1 by S square plus 2S plus 1. Okay, that's S is converted into Z domain. So S domain is converted into digital domain. Okay.
Okay, sir. Okay. Thank you, sir.
Okay, ma. Now we will go for the advances in the DSP. Number one is the signal modeling. So signal modeling means here what you can say the bandwidth, as I say the signal compression. So without reducing the bandwidth, I need to transmit the signal effectively. That is signal modeling. Then we have a optimal filtering. So optimum, two things are there. Optimum. So optimal means here, this is optimal means suppose I am staying in Warangal, and from Warangal I need to go to Hyderabad. There are different modes of travel are there. From Warangal, I can go to Hyderabad by train. I can go to Hyderabad by what you can say by bus, by car, and the other particular mode is by walk also I can go. So but optimal means here there are n number of approaches to reach destiny, that is to reach Hyderabad. But the optimal method is whichever will give the what you can say effective way. So effective means here the time within a less time I should reach there. So that's what from here Hyderabad to Delhi. Suppose if you take a train, it will take minimum 24 hours. Then if you take a flight directly within 2 hours, I can reach Delhi. So then which is effective method is I can go by a flight. But in terms of cost, the flight will be more, and in terms of cost, the train will be late. There, depending upon the application, so depending upon the specifications, so whichever the approach will give the optimal solution, then that is called the optimal filtering. So there are different types of optimal filters are there. Especially two types of optimal filters are there. One is Weiner filter, another one is the Kalman filter. So Weiner filter is a what you can say open loop filter and open loop system, and recursive filter, sorry, non-recursive filter, and Kalman filter is a recursive filter. So recursive filter means here we need not find out the each and every time the update the measurements. So suppose if you find out the current estimate, then I can find out the the result. So that's why Kalman filter is a recursive filter. Weiner filter is a the non-recursive filter. So signal modeling, optimal filtering, then spectral estimation. Spectral estimation, as I said, there are two types of estimations: parametric, non-parametric. In the case of what you can say the parametric approach, we can use the different types of non-parametric approach. We can use the what you can say different types of advanced window techniques like Bartlett window, then the Welch method, then Blackman and Turkey approaches. So basically here, the when did you say that a good estimator? When did you say that a good estimator? Good estimator means here, so the error, whatever we are finding, that error, what we can call it as a bias. So the first one is, for a finite period, the bias should be minimum. For a finite period, the bias should be minimum. Then the second one is, it should be applicable to the infinite length. It should be applicable to the infinite length. And it should provide the unity gain. The probability density function must be unity. So these are the features that if any particular estimator provides, then that is called the what you can say good estimator. So these concepts we will try to discuss in the case of spectral estimation. Then in the case of parametric estimation, there are three models are there. Everybody knows that fundamental three models. One is automatic auto-regressive method. Then second one is moving average method. Third one is ARMA model, that is auto-regressive and moving average model. Any system that we can represent in terms of input and output. From the input and output, I can represent three different approaches: auto-regressive, auto-regressive moving average, and another one is the moving average. All these things that we will try to discuss in the case of the spectral estimation. So signal modeling, optimal filtering, then spectral estimation. And next, fourth one is the adaptive signal processing. So in the case of adaptive signal processing, as I said, if the signal is a random signal, I can go for adaptive signal processing. So I'll try to discuss if time is there. So this is another one. Then multi-rate signal processing. So if the sampling rate, if you want to change the sampling rate, okay, then I can go for multi-rate signal processing. Then third, last one is the speech processing. So like this, we have different types of areas, advances in the case of DSP. So these are some of the advances, as I said. Then apart from that, we have a biomedical signal processing. Then we have a radar signal processing. Then image processing. And I told you that different types of fields. So in each particular field, we have different things. Now coming to the general applications of signal processing that I'll try to discuss. Okay, so those are the advances, and now I'll try to discuss about the general applications of signal processing where I can use this particular signal processing. So for engineering applications, robo, okay, we can use it. Okay, these are the actually to know the wind energy, we can use this particular thing. And for GPS applications, we are using this particular signal processing. Then this is actually the traffic light controller. Okay, so we can find out the here traffic lights, and this is actually one particular the stop bar detection. Okay, so when the people are coming, depending upon the traffic, so different types of sensors which we can keep, and for 2 minutes it will try to stop that. So all these things in clouding, we can connect to the cyber station, and they will try to monitor these things. That's why these days actually, so if anybody cross this, automatically chalana will come. So earlier actually last semester I worked as a visiting professor in AIT Bangkok. So in AIT Bangkok, they developed one AI based signal detection in their security gate. Okay, so and not only security gate, so they will try to identify the vehicles, whether the vehicle is a authorized registered vehicle or not. So they will try to take the scan shot of all the images of that particular, what you can say, the vehicle number, and this particular vehicle number they will try to process, and whether it is a registered vehicle or not. So directly the RTO people, they will get that particular information and they will try to process. So then this is another one is in bridges actually. So bridges, when train is going in the deep forest, so they will keep the sensor, and if the bridge is actually the strength is damaging, automatically it will give the indication remotely. Okay, this is actually using the artificial intelligence and expert system technology. The AI sensors detect and quantify the fatigue crack growth in the real time. So whatever the fatigue crack that occur in the railway line, so they will try to find out. So information is forwarded to bridge engineer via wireless network or satellite transmission. Then, so automated intelligent decisions are made from the data and displayed. So they will use some particular strain sensors to detect the approaching trains and wakes. Then application of the signal processing in the air traffic control system. Even in the case of air traffic control systems, we can use this particular signal processing. As I said, the first signal processing, like radar signal processing, where air traffic control, we can use this. This is robotics. This is actually robo laser surgeries. People are using this particular robo. See here, this is optical signal processing, where we can do the surgery and different type of things. And this is the application of signal processing in engineering. Bioelectrical, the electrical signals generated by living tissues like nerve cells and muscle cells are called bioelectrical signals. So bioelectrical signal measurements from heart. Okay, so the basic unit of nerve system is nerve cell, a neuron. And the basic function of the neuron is to transmit function information. So this is actually skin, galvanic skin response. As you have seen, everybody now telling about oximeter. So from this is a simple digital device. So if you keep that particular oximeter to your finger, it will give the oxygen level. Okay, like that here, there is the device. So this is the electrography EOG. So retina. So all these things are the the applications of signal processing in engineering, in the bioelectrical signal, and in the case of the industries, also we'll use the application. These are the different types of applications where. So these are actually the computer numerically controlled missions where I can use these things. So free vibration response measurement. So in the case of image analysis and the computer vision, I can use this. So biomedical computer vision can use this. Real-time face tracking, I can use this. So in the case of computer networks, I can use wireless ad hoc, free space optical LAN, routing congestion control. So by using the queuing theory, random process optimization, search methods, simulation, implementation. So that's all about the signal processing and applications. Okay. Now, quickly another 10 minutes, I'll try to give an introduction about the adaptive signal processing. Is it okay? So any clarifications from this particular talk, you just ask me. So 2 minutes time, and after 2 minutes, I'll go to other slide. Okay. Hello. Is it audible? Hello.
Yes, sir. Yes, sir.
Yes,
Please.
sir.
You are
Okay,
audible.
2 minutes. 2 minutes for the next another 10 minutes. I'll give some idea about adaptive signal processing. But now, any doubts in this case, you just ask, and then quickly another 10 minutes. I'll try to give some idea about adaptive signal processing. Then I'll close. Anything you please ask. Otherwise, I'll try to go for the other one. Is it visible?
Yes, sir.
Hello?
Yes, sir. Yes, it's visible.
Okay, just 10 minutes I'll try to give about adaptive signal processing, then I'll
Okay, sir.
stop. So basically the filtering and filter and filtering. So filter is a device that processes the signal in order to extract the information about the prescribed quantity of interest. So as I told you that analog filter, digital filter, then when I have these filters, why do you want to go for adaptive filters? So here, if you see, this is useful signal and this is noise. So here, the signal and noise are separate. In such case, I can use simple filters, FIR, IAR, or the different types of analog filters I can process. Suppose if the noise is occupying this useful signal. The frequency content of noise varying with respect to time, then the problem comes. In one case, even worst case is if two frequency bands overlap. If the two frequency bands overlap, then in such case, the adaptive filters can help in these situations. Okay, so when to use adaptive filters means conventional linear filters are used where the signal and noise occupy the fixed and separate frequency bands. So conventional linear filters means here conventional IR, FIR filters are used where the signal and noise occupy fixed and separate frequency band. That means the coefficients are constants. If the coefficients are constant, then I can use this particular, what you can say, the conventional linear filter. But when the filter characteristics are to be variable and updated to the changing signal characteristics, the coefficients of the filter should vary and cannot be specified in advance. In such case, I can go for adaptive filter. So here if you see, this is the interference spectrum and this is the desired signal spectrum. So if the interference spectrum is dominating the desired signal, that is there is a spectral overlap between signal and strong interference, then there is a spectral overlap between signal and noise, then I can go for adaptive filter. Or if the band occupied by the noise is unknown or varying with respect to time, then I can go for adaptive filter. So what is this adaptive filter? An adaptive filter is a digital filter with self-adjusting characteristics and it adapts automatically to changes in the input signals. So which is having a variable filter, then there is update algorithm. So if you take this is input x of n, so if you apply the variable filter, there is estimated signal that is called desired estimated signal. This is the desired signal. So if you subtract these two, we'll get a error. So if our goal is this error should be minimum, this error should be 0. Suppose if this error is not 0, then that is fed to the updated algorithm. So from this updated algorithm, I can process. So here in the updated algorithm, we have a different types of algorithms: least mean square algorithm, recursive least square algorithm, Kalman filter. Okay. So the basic advantage of the adaptive filter is adaptive filter, we can use it as a noise canceller. So as I said, two the distinct parts: digital filter with adjustable coefficients, and adaptive algorithm is used to adjust or modify the coefficients of the filter. So signal plus noise that I have given, and this is the digital filter with some noise. So here we will get the estimate and we will try to process. So here if you see the two input signals xk and yk are applied simultaneously to the adaptive filter, and from this if you see the estimated signal sk cap equal to yk minus nk cap, that is equal to sk plus nk minus nk cap. If nk equal to nk cap, then my estimated signal is equals to original signal. So that's why the main objective of the adaptive filter is to produce the optimum estimate of the noise in the contaminated signal and hence an optimum estimate of the signal. So this is achieved by using SK cap in a feedback arrangements to adjust the digital filter coefficients via suitable adaptive algorithm. Again, this is also an interesting research area, that is using the suitable adaptive algorithm to minimize the noise. So output signal serves two purposes: as an estimate of the desired signal, as an error signal which is used to adjust the filter coefficients. So the output signal serves the, suppose if nk equal to nk cap, then directly the estimated the desired signal. Suppose if there is any error is there, then this error again it is fed back to the adaptive algorithm, then we will try to adjust the coefficients. So some of the applications of the adaptive filters are, so the first one is identification, determine the parameters of unknown system such as communications channel or acoustic of an auditorium, put filter and system in parallel. So adaptive filter, unknown system, so we can use these things. Okay, so this is, if the error is small, then filter response is same. Then the inverse system identification, application of adaptive the filter is inverse system. So you develop a filter that has inverse response to a given system, put the system and filter in series, then we can use it as an inverse system. Here parallel means it is identification. So series means series means we can use the inverse system. When the output error is small, then the filter is inverse characteristic of a system. So then prediction. So in this application, it is necessary to assume the signal varies only slowly over the time, delay and adaptive filter. So the three applications, one is inverse, the identification, system identification, system inverse system, then prediction we can use. And here I can say the adaptive algorithms, as I told you that LMS, RLS, Kalman algorithm we can use. So basically the Wiener filter is there, but this Wiener filter is a open loop system, as I said, non-recursive system. So this is actually the error performance surface. So this error performance, normally we can see this, the optimum weight of this particular thing is W opt equal to R inverse into P. So it's consisting of cross correlation, auto correlation. That's why there is a complexity is there. That's why we will go for adaptive algorithm, where we can update the thing. We don't use the correlation. So initially set the weight Wk of I equal to 0, 1, 2, 3, n minus 1, compute the filter weight output, compute the filter estimate, and update the next filter weights. So like this, we can use this particular LMS algorithm to process this. So this is one type of algorithm that I can use it in the case of adaptive algorithm. Okay, so there is another things are there, other LMS based fast LMS algorithm, recursive, so Kalman. So not necessary. This is just I told you that for idea. I have told that. Okay, so this is another domain, adaptive algorithm. This adaptive algorithm, which we can use it in the case of this 5G technologies, there is a different types of the problems, inverse system, the system identification, and then prediction, all sort of things that we will try to use it. This is just a glance of what you can say the adaptive algorithm. Okay, so that's all about the adaptive algorithm. So if time permits, I'll try to take, but not now. So my scheduled time is over. So now
Yes.
quickly 5 minutes. If you have any doubts to this entire talk, you can discuss with me. And my mail ID, I think you can see my what you can say the phone number and mail in my profile also is there. Or you can go through the site and you can contact me further if any clarification or any further research. You can approach me. Any doubts? Please tell me.
Sir, thank you very much, sir, for your informative session. We are very fortunate enough to have you in this session, sir. Thank you very much on behalf of AICTE and AICTE University, Warangal, sir.
Yeah.
Sir,
Thank
if
you.
it all participants, if it are any have questions, please ask me. Yeah, thank you, sir. Mostly we'll conclude this session.
Yeah.
We have
Thank you.
another session in the next few minutes. Sir, thank you very much, sir. Once again, thank you very much.
Welcome.
Yeah, yes. Thank you, participants. We have another session in 5 minutes. Please, all of you join for that session. Thank you.